Okay, so good morning. Thanks for being back once again early in the morning. I wanted to just quickly remind you, so my talk has two parts, one part on rheology and one part of microfluidics. So I would like to spend a lot of time today on microfluidics, but I have a tiny bit to finish on the rheology part. So I'll try not to take too much time on that and to continue. So one thing I wanted to clarify, so I need to go through things. I will not continue at this speed, don't worry. So there's one thing I wanted to clarify after the discussion we had during the last lecture about what is the origin of shear thinning. So most systems indeed that shear thin are not dilute systems, but my talk was really supposed to be about dilute systems. Most systems that show shear thinning are semi-dilute or even concentrated systems, as the curve that I showed to you about the spider silk. And in this case, the viscosity at zero shear rate increases much more strongly than linearly with the volume fraction. So the advantage of that is, and that was nicely pointed out by Michael, that if you indeed are in this semi-dilute or concentrated system, your zero shear viscosity can be very high compared to the solvent viscosity. So it's much easier to have a strong shear thinning because you have a strong difference in viscosity. And the example I cited, and I'm sorry I used an example which didn't really illustrate what I wanted to say afterwards about the xanthane solution, is actually also in a regime where we are already in a semi-dilute regime. And so what I just said is that indeed in this regime your zero shear viscosity increases much more strongly than linearly with C star, and you've talked about with the concentration, and you talked about this a lot I think during the last weeks. So it is more easy to observe strong shear thinning. But nevertheless the effect also exists in very dilute suspensions or solutions of fibers or rod-like polymers, as I explained to you, and the result that is shown here is a result from a simulation. So all the mechanisms I explained are actually represented on this simulation result, and there's numerical predictions and analytical predictions that tell you that also in this case you have a plateau at very small shear rate, and you have a decrease of the viscosity with an exponent of -1/3. Right? So yeah, so let me just comment on that. So what we cannot read from this graph actually is the real value of the increased viscosity, because the viscosity is scaled basically by the solvent viscosity and by something which is comparable to the volume fraction. The R is actually the aspect ratio, so it's a logarithmic correction that comes from the aspect ratio of the fiber. So just to tell you, the effect is there, but the effect is probably difficult to measure in an experiment. And I wanted to show you one experiment which I think is maybe the experiment that approaches the most the situation that I described to you, which are very beautiful experiments using FD viruses. So an FD virus is a microorganism which has a length of about a micron and can be very nicely approximated as a small rigid rod. And these are experiments from the group of Lettinger in Leuven. And they show also this plateau and then the shear thinning, but also their experiments are already in the semi-dilute regime. So I just wanted to clarify that. And then I will actually go relatively quickly over the last part of my rheology class, because Dimitris has talked quite a bit about that yesterday. So we talked a lot about shear. So what is missing in our characterization was the elongation. And I think I can pass quite quickly over this, because Dimitris has introduced the elongation of viscosity. He has also explained to you that in a Newtonian fluid the elongation viscosity is just 3 times the shear viscosity, which is the Trouton ratio, but in a complex fluid this elongation viscosity can be much quicker. I want to spend a little bit of time to tell you how we can measure that, because remember yesterday with Dimitri he had all these ideas where you have like a filament or something that you can actually roll around a cylinder and stretch, or clamp between two holders and stretch. But this, you cannot do that for a fluid. So this works for very dense systems or viscoelastic systems that are rather solid, but it will not work in our case. So people tried to create this stagnation point flow. So remember, the typical flow describing an elongation of flow is a stagnation point flow, which when we look at the streamlines looks like that. Which is actually the same that you would recover if you would look inside a slab that you stretch in one direction and that actually retracts in the other direction. So there's possibilities to create this in a macroscopic flow. You can put your solution of polymers in this device, you suck in fluid from two sides, and you create this stagnation point flow. For very dilute polymer solutions, it's actually very hard to get a good resolution of what you want to measure here. And also one of the problems is that depending on where your polymer enters the flow, if it goes directly to the stagnation point, well, in theory it will stay forever. However, if it enters on the side, it will actually spend only a very short time in the flow. So actually this device works well for polymer melts or concentrated solutions, but not so nicely for our system. So I wanted to show my first example of a non-classical rheometer. So actually, if you look at droplet detachment, and I will show you here something that doesn't have a polymer, hopefully, and here's something that has a polymer. We'll see. I think the films have maybe started, yeah. So it's a droplet that is extruded from a nozzle. I will first let you. So here, this one is already broken. Okay, so what you can see here, and I will actually show this on the next slides. And before I explain in detail what I see here, I actually have a mystery to resolve with Frédéric. Because those who have been at the public lecture have seen these pictures in Frédéric's lecture. And I would really like to know how they ended up there, because these pictures are actually pictures that students took in a lab class. And I found them so beautiful when they handed in their report that now I use them in all my talks. And I didn't know that they became so famous that now they are also in Frédéric's talk. And I'm really, really sorry that I don't even remember the students who did this, because I think now we should really give credit to them. But maybe I'll find out, and then we can put the names. So what I wanted to show here is actually, if you look at the detachment of something that is only water compared to the detachment of a polymer solution. And once again, this is the flexible polymer, and we put a really small amount of polymer into the water, like 200 ppm. So the detachment of water is, first of all, extremely quick. And so here, this has been done with a fast camera, and the differences are actually milliseconds. You can actually see that you have this neck that forms. So the droplet is extruded from the nozzle. So first of all, gravity pulls on it until you form this thread. And when you have the thread, actually the surface tension takes over. And surface tension pinches the thread. And in this case, it's actually inertia that resists. And people were extremely interested into this phenomena, because look what you see here. You see this very sharp cone that is actually forming here right before detachment. And that is extremely unusual. So if you remember the discussion about the surface tension, normally surface tension is there to make things round. So this is something that normally in nature nearly never occurs. And there has been a lot of theoretical analysis around this problem, and people could show that this is a very special instability. So it's a singular point in time and space that leads to the formation of this cone. So the advantage was that people had investigated this system a lot before people started to put polymers. So we knew the base state extremely well. And so you see, if you put the polymer solutions with a little bit of polymer, the situation changes completely. So the thread that forms is very, very, very stable, and you can basically observe it forever. And so people thought, maybe we can use this to characterize the properties of a solution under extension. And the graph I will show now is again from Gareth McKinley's group, and you can identify two very different regimes. So first of all these detachment experiments, your time reference in time is actually the pinch, so when it actually ruptures. So we have a time before the pinch, and then we have the pinch. And so this is for water, and actually you can show that in this regime it's a competition between surface tension and inertia, and that actually the radius changes over time as a power law. Okay? And what is interesting, that actually this radius, due to the fact that it's like a power law, it accelerates more and more and more. So that means if you look at the thinning dynamics, and this formula has also been shown yesterday by Dimitri, that the epsilon dot will actually increase in time while you walk through this graph until it diverges at the detachment point. So now if you put a little bit of polymer, you see that in the beginning you will follow this curve which is given by the pure water, and at some well-defined radius you would actually transit to another regime. And this is the regime that we saw, which is very strongly slowed down, where the thinning of the filament really takes a long time. And in this case, actually, the elongation viscosity sets in, and what we have is a competition between surface tension and elongation viscosity. So maybe this reminds you something, because we said that actually non-Newtonian properties will set in above a certain critical Weisenberg number. So our solution has some relaxation time lambda, which can, for example, be the Sim relaxation time that we discussed already. And while I walk through this curve, so while the thread is thinning, my epsilon dot goes up. So actually, I will have a Newtonian fluid until I reach a critical epsilon dot, and I have maybe indicated that at this point, until I reach a critical epsilon dot where my Weisenberg number will be larger than 1, and then I will manage to stretch polymers, and I will feel the non-Newtonian effects and will transit to this curve. So the first thing we can do with this kind of experiments is get an idea about the relaxation time, which is already something that is very interesting to do. But the second thing also is that it turns out that nature is very kind with us, so this decrease, the dynamics of this discrete decrease, turn out to be exponential. So remember yesterday when Dimitris introduced these fiber stretching apparatus, he told us if we want to have a constant epsilon dot, we need actually to stretch with a velocity that, with a displacement that increases exponentially. So here, the nature builds us a thinning dynamics which creates a constant epsilon dot in the thread. So not only it is a system where we can use the point where actually this graph diverges from the graph of water to get the relaxation time, but we also have now a thinning dynamics here in a perfectly elongational flow. And so the second thing you can do, you can actually use this part and equilibrate the surface tension with the elongation and viscosity to get a quantitative measurement of the elongation and viscosity. Okay. Yeah. So these solutions are very dilute polymer solutions, so they have a Newtonian viscosity. I don't know, shear thickening, people did actually droplet detachment with cornstarch, and the dynamics are completely changed. They're actually really interesting because you have small parts of the thread that are jammed, and then the thinning gets very localized at other parts. So I'm sure people did also shear thinning fluids. I don't really have the experiment in mind, but I would suspect that also localization takes place much faster, because if you locally start to detach a bit faster, your viscosity will go down and will accelerate things. But people have also put particles in there to disturb the dynamics, so you can do many, many things actually with these dynamics. Okay, so maybe I'm not saying much more about that, but I wanted to show you one thing. So this was actually, I think, a very nice way that a lab experiment started to be used to have a characterization that became quantitative, and people wanted indeed to make a rheometer out of that, but it's really not very convenient if you have this very, very, very long thread. And also you need a fast camera, so you need to have a very good focus on your thread, but on the other hand, you never know where actually the most thinnest point of your thread is. So people designed something that they call a caber, a capillary breaker rheometer. So it's exactly the same experiment than if you put your saliva between two fingers, you open it a little bit, you form a thread, and then you see what happens. And that normally should happen here. Yeah. So you form the thread, and then you just observe the thread. And this is very comparable to this filament stretching rheometer that has been shown and can actually be bought commercially. And there, once again, you would actually look at the thinning dynamics with a laser. Okay. Yeah.
Sorry, what exactly happened in the video? I did not
sorry. Yeah, because there's important things you cannot see in the video. So basically, in the video, there's two plates, like here. The liquid is between two plates, and you actually stretch these two plates in such a way as to form a filament. And once the filament is formed, you do not do anything anymore. The surface tension takes over, and all the dynamics are given by the surface tension. But let me just show it again. Oh. So here, the two plates are pulled apart, and once the filament is formed, we start to do our measurement. Okay. Was another question, or? Yeah, so the plates are really only there to produce the filament. It's very different from the filament stretching rheometer, where actually the stretching is given by the plates that move apart. Right. And there's many things, I mean, you try to move it apart not too fast, not to pre-stretch your things too much, etc. Yeah, and so by doing this, you can indeed measure elongation and viscosities, as are shown here, which typically have this Newtonian part. which should just be 3 times the solvent viscosity. At a critical Weissenberg number, they will increase until they saturate, because their saturation is there because at some stage you have stretched all your polymers and you cannot do more to your system. Okay. Okay, so that was a little bit fast, but I actually wanted not to spend too much time on the rheology part, but I will still conclude on this part by, well, completeness. You remember we had this spider silk, and I showed you the real shear thinning viscosity curve of the spider silk. So for this work, they also did extensional rheology. So here you can see a tiny Caber experiment. And what they saw, if they look at the thinning of the radius, is that in the beginning, the radius thins quite quickly, and then they actually, at some stage, nothing happens anymore. So this corresponds to a very, very strong strain hardening while you pull on your thread, and that is what is shown here for the extensional viscosity. So in this case, they also think that at some stage the sample will dry and it will really solidify. But it's also in equivalence to what Dimitris told you, is really you have specific properties of a material for specific purposes of the material. For the spider, it's very important that you can actually squeeze out the silk very easily. So when the spider squeezes out the silk, the viscosity needs to be small. So strong shear thinning is important. But once you form the thread, it's very important that the thread gets stable very quickly. And so that's what happens with the strong shear hardening or extension hardening. And I think I owe you one last thing, is that I told you that we want to link always the microscopic dynamics to the macroscopic property. And I already mentioned that when we have these elongation flows that we pull on filaments, but indeed people have observed this on the microscopic level. And these are again single molecule experiments done in the group by Stephen Chu. And actually these were done before the shear experiments that I showed you. So what you can see here again is DNA molecules fluorescently labeled, so a very flexible polymer that if you don't pull on it is in a spherical shape. And what they did is actually they used a microfluidic device and they put the DNA molecule at the stagnation point, and they tried to hold it there as long as possible to see the dynamics. So these are actually very beautiful and very clever experiments. They're not simple at all, because as soon as you have a small perturbation in your system, I mean, you will use your DNA molecule. But by doing this, they could actually see how the coiled filament would be stretched. So proving the idea that it's the local stretching of the polymer that gives these viscoelastic properties, but they also highlighted that this stretching is far from trivial. So you can see you can get many different shapes. So here you can see it's stretched in the middle, a little bit coiled still on the side, or it can remain coiled on one side and only be stretched on the other side. So there's actually very, very interesting dynamics on the single DNA molecule underflows. Okay, so with this I will stop and conclude my rheology part, unless you have some questions then on that. Yeah? Yes? Yeah. Oh, if I would like to align, I think it's always more efficient if you have extension, because if you have extension, you can actually pull on the same molecule for a longer time, so it will stretch more. But shear also aligns things, so if it's only the question of alignment, the problem is in the shear you can tumble for a long time, so I think stretching is actually more efficient to align things. But if you're quite concentrated, shear aligns very well also. Yeah, there was another question, yeah? Okay, so you say, why do I call this elasticity? Yeah, so actually, first of all, I was calling it elasticity because we know that the polymer is elastic. So we know that if I pull on the polymer and I will let go, the polymer will retreat back to its initial configuration. And I think that you discussed this probably a lot when you talked about polymer dynamics. But you can also do experiments. I mean, first of all, these G' G double prime experiments, which are in the linear regime, which is not exactly what we do here. Basically, you make a deformation and only and part of it will come back. So, yeah. So in extension, for example, if you have something that is really, really very viscoelastic, if you would, I don't know, make your thread and you would cut the thread, I mean, it would actually snap back. Okay. So there's really a part of elasticity in the system. You stretch locally the polymers, and if you let go, the polymer comes back. It's true that we are in a very dilute system, so it will really act still as a fluid, and mainly what you will see are these normal stress differences and an increased resistance to stretching, but these are really elastic effects. Yeah. Okay. Okay, so if there's no more questions, I would like to go now to the part where we talk about flow. So we have talked up to now a lot about rheological characterization of these viscoelastic fluids, but we have not really thought about how do these properties influence flow. So basically what we had this constitutive equation, which as we discussed is something quite marvelous because it allows us to link arbitrary stresses to arbitrary flows or arbitrary flows to arbitrary stresses, but it doesn't really tell us how this flow came about. So we don't really know why or what forces were necessary to create this flow. And typically to create a flow, what we do, either we impose a boundary condition, and we have actually discussed this also already quite a lot about local friction and the fact that you normally, if you don't have slip, have a zero velocity boundary condition here, so you can impose flow, for example, by having a device where the upper part would rotate. But of course, you can also impose flows by applying forces or stresses directly to the system, like by applying, for example, a pressure difference and a capillary tube between the inlet and the outlet. And the next thing I want to do is to actually explain how do we link our constitutive equation to the momentum balance equation, which is the Navier-Stokes equation. So how do we create flows? And then I want to discuss how these flows are modified for non-Newtonian fluids. So the Navier-Stokes equation, you've seen it already yesterday with Frédéric. I don't want to spend or to have you look in too much details at the formula, but I would like you to understand what the Navier-Stokes equation is. So the Navier-Stokes equation is a momentum balance equation. So it's really an acceleration on one side and all the applied forces on the other side. It's just that here actually we talk about fluid elements and we will actually look at forces per unit volume. On the left side, so you have the acceleration. So the acceleration in a fluid looks a little bit complicated because you can accelerate due to two reasons in a fluid. If you stay locally at the same position, your flow can change over time, so you can accelerate, but you can also be transported through the flow from a part where the velocity is small to a part where the velocity is high. So this is why the acceleration term actually looks very complicated. The acceleration term is where all the nonlinear parts of fluid mechanics come from that creates turbulence and instabilities and is studied a lot, but I already tell you that we will not be concerned with this part. And then here you can have different types of forces or stresses that you apply to your fluid. You can have what we call volume forces like gravity that will act everywhere on the fluid. You can have surface forces like pressure. And here you have the viscous dissipation. So if we forget about the inertia, what we will balance is the viscous dissipation with the applied stresses. And that already sounds a bit familiar to what we thought about the stress tensor. But I want to make a small detour to explain you why and when can we neglect this acceleration part. And I think we've quite heard a bit about the Reynolds number already in the different lectures. So the Reynolds number is something that compares inertia with viscous dissipation. So basically it compares as a scaling argument the acceleration part with the viscous dissipation. So if we just use density, velocity, length and viscosity, you can actually see that the inertia part is proportional to density, velocity, a spatial derivative and velocity again, so rho v squared divided by L. And on the other side, the dissipation part is the viscosity, velocity, and a spatial derivation to the power 2, so divided by L squared. So if you put that together, you end up with the famous Reynolds number. So when the Reynolds number is small, it means that the viscosity completely dominates so that your system is completely overdamped. Okay? And this happens, for example, for very viscous fluids, but it also happens for very small scales. So all the things I will discuss about in microfluidics will actually be at small Reynolds number because they have very small scales. And so in this case, you end up with something which is simplified. This is actually the Stokes equation. So we actually get rid of the acceleration part. Let's just say we don't have gravity. I would just be concerned by things where I apply a pressure difference, so a pressure gradient. So basically, I only balance the pressure gradient with the viscous dissipation. So that's very nice, and that's actually the form that people work with a lot. But I mean, how did actually this viscosity enter there? And we also know that sometimes we do not only have the viscosity, so what do I do if I have actually a fluid that is more complex than just a Newtonian fluid? And so we can go one step back, and if you go one step back, actually to build the momentum equation, it's not that just by chance this term falls from heaven, but it actually comes from a term where we indeed balance the pressure gradient with the gradient of the stress tensor. Okay? And then if you rewrite that using the constitutive equation, you end up with this Stokes equation. So we need to keep in mind, if we want to work or have to work with non-Newtonian fluids, we should look at an equation, at a Stokes equation, where we use actually this stress tensor and not right away the viscosity here. Okay? But we can now also understand how we link what we've learned about the stress tensor to, for example, an applied pressure difference. Are there questions or? Yeah, okay. And I want to remind you again that this formula so only works if we have the constitutive equation and if we work in incompressible fluids. I want to spend a little bit of time on the exact solution of flow in this capillary tube. So it's also an example you've seen quite a bit already. It's actually a very, very important flow geometry because it occurs a lot. It actually occurs much more than the simple shear that we have cited. So pipe flow, blood vessels, channel flows. So many, many, many situations where you have flow are actually something that has some kind of walls and boundary, and you would apply a pressure difference to impose flow. Just for simplicity here, we will use the capillary tube, which is circular. So what you now need to do is that, let's look at these Stokes equations. So we start with Newtonian fluid. This is actually a 3D equation. I mean, we have x, y, and z, or we can work in cylindrical coordinates. So we need to find out what are the components that I need to use of this equation to solve my specific problem. And that can be done by using the geometry. So what we can see here, for example, that we expect kind of right away that the velocity will be along this axis, because this is where I impose my pressure difference, and that velocity will vary with the radius when I go in this direction. We can also understand that velocity will not change along the tube because my fluid is incompressible, so it cannot locally accelerate and decelerate. So there's some things about the symmetry of the system that I can put into my equation, and by doing this I can actually simplify things and I end up with an equation to solve. But I can also look at the problem from another side. So what I know is that actually this momentum balance equation comes from an equilibrium between the pressure gradient and the viscous dissipation. So I can also look right away at the right fluid element. So I can actually look at a small cylinder. So my idea is I have a small cylinder where the inner cylinder slides in the outer cylinder, which is basically what happens in this flow geometry. And I can just write the pressure difference on this small ring on the left and on the right side, and I will equilibrate it with the viscous friction on the cylinder. And by doing this, I end up with exactly the same equation. So there's really meaning to all of these equations that we see that are very closely linked to the geometry. And now once we have the equation, we can actually resolve it. And just for completeness, I have written it there, but I will hide it now. But it will be on the slides, so if you want to see it, you can see it. But it's a very standard calculation, so you just integrate and you use your boundary conditions where the velocity needs to be 0, and you end up with a very famous solution, which is actually the parabolic flow profile of Boiseuil flow. So basically what is important to see here is that the velocity is along the x direction, it varies with r, it has the pressure gradient here, has 1 over the viscosity, and it's quadratic in r. Okay? So this is not a very beautiful drawing, but this is actually a parabolic flow profile. So what is important to note here, that now we are not in a situation of a linear flow anymore. So now shear rate actually varies throughout my sample. So the shear rate is maximum. I should show this here because this drawing is really very bad. So shear rate is maximum at the boundary and is actually 0 in the middle. So I have a very strongly varying shear rate, and also it changes sign from one side to the other side. So Boiseuil flow is a quite specific flow. What you can also do, and this is for practical reasons where you want to use this, for example, to measure viscosity, you can actually integrate over this velocity to get a flow rate, to have the flow rate Q. And this is also a very famous result. So the flow rate is just the volume over time, how much water comes out of your tube over time. And this is actually proportional to the radius to the power 4. Okay. And this is really used to measure viscosities, for example. So this is really an example where we see that the fact that we have this boundary condition where the velocity needs to be 0 all around with the applied pressure gradient leads actually to this flow profile. Okay. So the next step I wanted to do is, so now I have this flow profile, but what happens, for example, if I have a shear thinning fluid? How is this flow profile modified? So if I have a shear thinning fluid, so what I need to do, so keep in mind, now the equation I need to solve, I need to be careful, I need to go one step up and use the equation written as a function of the stress. So it's the same equation. It's exactly the same equation as this one, it's just only that I wrote it one step up with actually the stress tensor. And I also know how this stress tensor looks like because I want to input a shear thinning fluid and I want to make my life simple, so I want to use a shear thinning fluid with a power law dependence, so I know exactly how my stress tensor looks like. And if I input this and do all the calculation, I end up with a formula that looks a little bit more complicated, but it was actually a bit like we expected it. We input a power law, so actually what we get is a change of the exponent of the dependence of the velocity with the radius. And how does that look like? So I'm sorry again about my drawing. So first of all, if you do this kind of calculation, the first thing you do, you check if you recover your Newtonian limit. So we know for the power law fluid, if n equals 1, I should recover the Newtonian liquid, and indeed, luckily, that's the case. For n equal 1, I recover the parabolic flow, which is the blue curve. And mainly, I wanted to insist on the green curve. So the green curve is for the shear thinning fluid, and what you can see that this parabolic flow profile is actually deformed by the effect of the shear thinning, and you get something that looks a bit more like a plug flow. And it's a little bit like what you saw on the shear bending yesterday. I mean, the shear bending is the extreme where you really have two different phases, but you saw that actually shear became localized close to the part of the quad that was moving. And that's actually the same thing here. So the fluid adapts in such a way that locally he creates a higher shear rate, and a lot of parts have a very small shear rate. That means it's a little bit like creating a lubrication layer on the side to push your fluid through the tube faster. And I think it also illustrates again this non-linearity of what we are doing. So by changing the fluid properties, I have also changed the flow profile. And it indicates that if you want to do rheology and you know nothing about your fluid in the beginning, working with a flow that is more complex, so with a flow where locally the shear rate can vary, puts you in a situation where you don't really know what you will be measuring. As long as you have a simple geometry in a rheometer with a constant shear rate, all is perfectly fine. Because if you have a constant shear rate, the flow profile will not be changed and will stay linear. But here you need actually to be careful about that. Okay? Good. So, yeah, please.
Sorry, I don't understand. You think a step, how do you go from eta is proportional to gamma n minus 1 to sigma is proportional to gamma dot n?
Okay, so the definition of the viscosity is just, it's the stress divided by the shear rate. So it's the same constitutive equation, it's the same, the power law fluid, either the viscosity is this or the stress is that. It's just a definition. Yeah, it's like this. Basically that would be the better definition to start with, and that's also the one that has an exponent that makes sense. And just if you, the shear viscosity is defined as stress divided by gamma dot. Okay. There more questions? Okay. And so now I have reached finally the part I wanted to talk to you about, the microfluidics part. So now we have heard a lot about rheology, mainly dilute systems. We have learned how these properties change flow. And what I want to do now is I really want to spend the rest of the time that we have to talk about microfluidics with different aspects. So the first thing is I want to convince you or explain you what are the specificities of microfluidics and why they can be really interesting to look at complex fluids. So I think there has been quite some posters on microfluidics, and maybe you are already familiar with microfluidics anyways, but microfluidics are actually things where we have flow geometries with typical sizes of 100 micrometers in width. So it's typically the size of a hair. So you need to imagine that everything you're doing is that you're looking at flows in the size of one hair. The advantage, well, there's many advantages, is that we know that the Reynolds number will be small, so we have no inertia in our systems, so that also flow will always be laminar. When I'm working in a situation of laminar flow, basically by designing my flow geometry, I know that the fluid will follow this geometry. So I have a very easy and a very perfect flow control in my systems. So that's first why it can be really interesting also to do rheology in these experiments. Well, obviously, we need very small sample volumes, so all these ideas on lab on a chip come from the idea that I can actually work and manipulate very small sample volumes. What is also really nice is that the simple process of fabricating them, and I will show it to you on the next slide, involves typically PDMS or other transparent materials, so it's very easy or very well adapted to observe directly on a microscope what happens inside the channel. Compared to most of the rheological geometries which are made from metal, this is actually a very big advantage. And then maybe this is a disadvantage. It's a channel, so I will always have porous flows. So from this point of view, I'm relatively far away from a perfect rheological flow situation. So going through that, there's actually two types of rheometers that I want to present to you. There's the first one, which is actually quite standard, but using a microfluidic rheometer. So if you go back to the classical result of porous flow, basically if I want to use porous flow to measure viscosities, I measure the flow rate and the pressure gradient, and what is proportional in there is the viscosity. So if I can do that on a big scale, I can also do it on a small scale. But then I also want to show you some rheometers where people thought about something different, a bit like the idea when we had the droplet detachment, where instead of ourselves pulling on the system, we use the surface tension to pull on the system, and show you some ideas which I think are quite nice ideas how I can work with these systems. And here I copied a number of recent reviews where people describe different things you can do if you want to do rheology in microfluidic systems. So first, I want to do a small detour to explain to you how we produce these channels, because this is also really one of the important advantages. It's a method that is very versatile and very fast. So if you have an idea on the geometry that you want to design, from this idea to the real channel that you have in your hands is quite fast. Obviously, it's still work to do, but compared to making something big in a machine shop, you can change things very fast. So the basic idea is that you draw something on a mask. You have like a resin, which is photosensitive, that you would spin coat on a wafer. So you take the wafer, you spin coat the resin on the wafer. You have a resin of a certain height, typically some hundreds of microns, and then you shine UV light through the mask. So locally, the resin will harden. But only where you have been shining UV light on it, you will actually rinse the resin, and you will have like your negative, okay? And then on this negative, on the master, you will actually pour the PDMS. So PDMS, I'm sure you all know better than I what it is, and you actually put it in the oven, it will cross-link and form an elastomer, and then you just peel it off, and you will actually glue it on a glass slide. And then you need to make connectors, and you have your channel device. There's many, many more methods that have been developed recently. You can locally use a nano printer. You can combine PDMS with other materials. You can do this in plastic. You can do this in glass. So there has been a lot of development about microfabrication, and maybe Sam saw Jubo's poster where he also explained many things we tried to make this more versatile. But this is the standard method and actually works quite nicely. So let me start with some examples on measuring just viscosity using these channels. And this is what I already told you. So it's the standard way, as in the porous flow, just we adapt the equations to a square channel. We measure flow rate and we measure the pressure gradient. So there's different ways to do that. Maybe let me just start with this one. So, well, everything now is about the question of how do I measure things. So I have very small volumes. I probably have small pressures that I apply, and my flow rates might also be relatively small. So everything now depends on how can I measure flow rates and how can I measure pressure differences. So one example here is shown on how to measure velocities. So it's actually thermal flow sensors that measure what is called a time of flight. So you have a signal that is given here, a thermal signal, and you will see actually how long it takes for the signal to be recovered a little bit downstream in the channel. So this allows to measure average velocities, and you can link them to the pressure gradient that you applied. Yeah. Oh, so actually here the pressure would be applied from here to there. So sorry, this is a channel where you look from above. So maybe we can try to use that as an example. So if you think about the channel like in this way, you have an inlet, you have an outlet, you have your square channel here. And what is done here is that I would look from here. And what you can see is actually these sensors that are embedded in the top plate of your channel. Okay? The gray parts, yeah. So or the white, yeah. So these are actually the sensors. So it's what we call a MEMS. So it's actually you combine microelectronics with microfluidics. Okay? And so it means that you can locally emit a stress thermal signal, and then you can recover it a little bit downstream. Okay? So this is something that allows to measure average velocities, but you can also take advantage of the fact that you can look through your channel and you can measure local velocities. Now we are looking actually in the from the side at the channel, and if you look from the side at the channel, you will recover this parabolic flow profile. Maybe I'll just make a quick drawing of the channel because I think it's kind of missing. So our channel typically looks something like that. So it actually here, this is these 100 micrometers height. This can be much larger. This can be, I don't know, 600 micrometers, and there's more or less no limit on the length. So what will happen, what I actually showed you for the capillary flow with the Poiseuille flow profile, the Poiseuille flow profile actually here will occur in the small dimension. So if I have two plates, I have flow between the two plates, the parabolic flow profile will be between the two plates. And nothing will happen in the width. So actually the flow will be more or less constant everywhere here with a small adjustment to the side planes. Okay, so if I look from the top, I will not see the local shear, but if I look from the side, I will see the Poiseuille flow profile. Okay. And that is actually what people did here, what is shown here. So now we observe in the direction of the Poiseuille flow profile. And the nice thing is that if you're on a microscope, you can actually scan through your channel. So you can start on the bottom and you can slowly move through the channel, and you will locally measure the velocity with what is called a PIV technique. So a PIV technique is that you put many particles in actually your fluid, some tracer particles, and you take pictures at a very small time step from each other, and you will actually check where one particle on one picture has traveled to on the next picture. Okay, so you can measure locally velocities like that. And if you do this, you can actually locally resolve the parabolic flow profile, which is actually nice because it gives you more information. It gives, of course, also the average speed of transport, but it also gives you an information about the fact, is this a Newtonian fluid, is it parabolic, or do you have any kind of deviation from the parabolic flow profile? So if you do this, you already add quite some information to the system. So these are actually ideas that are based on flow rate measurements, but you can also, of course, do the opposite. You can impose the flow rate and measure pressure differences. And this is actually a rheometer which is called the MVROC, which came out of Gareth McKinley's lab and which now is something that you can commercially buy, where you impose a flow rate, it measures the pressure and gives you the viscosity. So to go a little bit further, so this is actually for a Newtonian fluid, but let's see what happens if I take a non-Newtonian fluid. And these are again measurements of this parabolic flow profile from the side in the small direction of the channel. And what you can see here, for example, is that it goes from something that looks Newtonian-like to something that is more and more flat for a shear thinning fluid. The nice thing is what people did actually is that they have a channel where you go from a large channel to a smaller channel. So locally you change your flow structure. So it's like these experiments that you saw yesterday where you suddenly turn on your shear or your stress. And to measure transient behavior in a microchannel, what is really nice that actually in a microchannel distance is equivalent to time. If you know your flow velocity, your average flow velocity, when you move down the channel, it basically means that the fluid has spent more time in the channel. So what they did here is that they actually measured right when you entered this tiny channel, and then further downstream, and they could actually show that it took a little bit of time for the fluid to establish its full flow profile, and that's what you can see here. So that's also something that you can do specifically in a microchannel. Take advantage of this fact that you can see how things evolve with time just by looking at different points in the channel. So this is when you measure directly the flow profile, but I just want to go back quickly to the fact that for many situations like here, you need to measure the pressure difference. So measuring the pressure difference actually turns out to be not as easy as one might think, because pressure differences might be really small. So there's many pressure sensors that exist on the market that work well if your pressures are a little bit higher, but it's quite limited when you go to microfluidic systems. And some people have started to develop a pressure sensor. So I will first cite this example, which I think is a very nice idea. So what they said, okay, I want to locally measure pressure in a channel, if possible, all along the channel. So now again, we look from above. You have a tiny microfluidic channel, and they connected these sensors to the side of the channel. So once your flow is fully established, there's no problem with these small side channels because no flow will happen in the small side channels. So you do not disturb the flow by doing this. And what we expect to measure is, so this is flow again, like in a Poiseuille flow in a capillary tube. So I have a constant pressure gradient. So I expect the pressure to decrease from here to there in a linear way. So how do they locally access the pressure? So they have a system, if you look at one of these pressure sensors, where they have a membrane, and this membrane can actually deform under the pressure of the fluid. And when the pressure is higher, the membrane will deform more. And then they have a way of trying to detect this inflection of the membrane. And what they do is, I think, a bit hard probably to do, but they actually look at the size of these white spots and they calibrate the size of the white spots, and then they link this to the amount of deformation and the local pressure. But it actually leads to a quite nice and linear dependence of the pressure as predicted. And what I wanted to show you now is actually a pressure sensor that we have developed in the lab in collaboration with the group of Jean-Ping Gong, where partially we actually were relying on this design principle. But what we did is that we actually used one of these color-changing gels of Jean-Ping Gong, and there's people in the audience that are much more specialist on these type of gels than I am. But for us, it was really fascinating when we started this collaboration, what fantastic things they can actually produce in Jean-Ping Gong's lab. So I will just show it to you again. So this is one of these color-changing hydrogels. This is when you do not apply any pressure, and what you will see is actually cyclic pressure that will be applied to the gel. I agree, it's really pretty. So what you can see when they just press with a glass slide, that you go from red to blue. You can also see, I think that's real time, that you can change the colors very quickly and that it recovers very nicely. So the principle is, for those who did not see the poster out there, that it's a hydrogel that is actually built with layers. So these layers are actually lipid bilayers, and they're relatively rigid. And between them is the hydrogel, which is very soft. And the distance between these layers are comparable to the wavelengths of the visible light. So now if you actually shine light on it, you have the Bragg reflection, and you will actually get the color that corresponds to the wavelengths of the distance between these layers. It's a way like beetles, for example, use this to produce color in their surrounding. And the nice thing here is now you can easily imagine if you squeeze this material now that you will actually reduce the distance between the layers, and actually the color will change. You will go from red to blue. And they can nicely tune this by actually making the hydrogel here more or less soft or more rigid, so that actually the response can be actually tuned by that. So when we saw that, we said, wow, I mean, this is really beautiful. So maybe we can use this and locally measure a pressure in a microchannel. So the first thing we did is actually that we calibrated one of these gels. I mean, of course, this has been done also for many other gels in Jean-Ping Gong's group. So what you do is that you apply a certain pressure, and you can measure the wavelengths. If you want to precise, you can measure the wavelengths with the spectrometer, or you can just use a color camera. And you can actually see that you have a linear relationship between the color and the applied pressure. So once we had that, we said, okay, now maybe let's just try now to implement this in the microchannel. And we used the same design principle as the one that you saw before. And these beautiful animations have been made by Martina, my postdoc, so you can see that it's not me who did them. So we actually said, okay, let's try to do the same as we did before. We have actually these small sensors on the side of the channel. And the principle is the following. So what we will do is that we will actually take the gel, we will embed the gel in some kind of PDMS pool, and then we will cover the gel with a soft membrane because we actually want to separate the gel from flow in the channel. And then on top of that we will put a fluid cavity, and the fluid cavity will be connected to the channel flow. So when the pressure in the channel gets higher, the pressure gets higher in the fluid cavity and will actually press on the small membrane. And that's what you can see on the next figure. So when the pressure gets high, we will actually push on the membrane, the gel would get blue. When the pressure is small, the gel will remain red. And then we just observe this in reflection from the top or from the bottom. Yeah. It's a very, very hard question. You can maybe talk to Jubo about that. It's one of the main problems about microfluidics, or it's one of the problems. There's many tricks. You fill your syringes before you connect, you apply a little bit of overpressure and it diffuses through the PDMS. It depends also a lot on your system. But I would suggest if you want to talk to Jubo, who has handled a lot of bubbles, and with time you acquire a number of practical tricks. But yeah, it's a very it's a problem in microfluidics, because once you have a bubble, I mean you're done. Yeah.
What is the material of the cavity wall?
So right now what we do is that we actually have everything in PDMS, but it's not a requirement. It's just because for the way we produce our layered system, it was the easiest thing we had, but you could have a plastic or a glass. What is important is that this small membrane, so for the moment also the membrane is PDMS, it does not have to be PDMS, but it needs to be something that is thin enough so that it's actually deformable. Because, I mean, what really makes the system also interesting and tunable is that, of course, I said I only talked about the gel, but in reality what you have here is a combined system. So you have the gel that you will deform, and also it's not really semi-infinite, so it's a slab of gel. And on top you have the membrane that you deform. So we have situations where actually this cavity is very large, so it can be some millimeters. And in this case, actually, the membrane nearly doesn't play a role because it's very thin and it's very easy to deform. And we really measure the modulus of the gel. But we can make the cavity smaller. So if you make the cavity smaller, actually it will become hard for the membrane to deform. And what we will measure is the coupling between the membrane and the gel below. So we actually need to calibrate, or we could also calculate, but we need to calibrate our system for each size. But it's nice because it allows us to go from a sensor which is very sensitive, because the modulus of the gel is as small as possible, to a sensor that is actually much less sensitive, that can go to higher pressure ranges. And, yeah.
Is the membrane porous? I mean, like, there's something diffuse out of the membrane and the gel swells?
So, yeah, no, we try to avoid that. So the idea is really that I separate fully the flow in the channel from the gel. But what is important to note is, and I'm not sure if you can see that it's actually not completely shown, maybe it's shown on the next transparency. The gel needs to be in the buffer solution. So we actually need to have a possibility to hydrate the gel, and in reality we have an inlet and an outlet, so that actually we can assure that the gel stays as the gel likes to be in the buffer solution. Yeah, but I actually have a slide here. So how it looks in reality. So this is our proof of concept. So what is, again, now we see from above, you have the channel here. We have these small branches to the side. And in this case, what we did, they actually just used a long slab of gel. So you have a long slab of gel on the left and on the right side. And on top of that, we close everything with the membrane. And then we put the channel and these cavities here. And you see the large cavities, which are like 2 millimeters, and the small cavities, which I don't remember exactly how large they were. And then we just impose flow, and we measure the pressure difference. Yeah.
So you can do the air pressure inside the chamber, or the gel is constrained within the PDMS, so the pressure may shift differently. And you said you calibrate it, but how do you calibrate it without using other methods?
Yeah. So it's true, we need to know how to calibrate. First thing, what I wanted to say, that yeah, the gel is constrained, but we take care of the fact that the gel is actually free on the sides. Okay, there's a little bit of space on the side, so I can, if I push on the bottom, the gel is free to go on the sides. And how we calibrate is that basically we do not use a fluid, so we fill the full channel with air, and we have actually, we can apply a given pressure, and we calibrate this pressure. I mean, mostly all pressure sensors you buy, you would calibrate them also at some stage. Yeah. So what you can see here nicely is if you apply a flow that you indeed go from a higher pressure, you can see that this is blue to green to red on these different sensors here, and you can recover the linear pressure profile that you were looking for. And I think that the largest pressure point here has actually been done in a small cavity, and the other one has been done in the large cavities. So we can really show that we can go from one range to another range with this system. Okay, are there more questions? So it was kind of a small detour. I will make many detours in the rest of my talk to show how you can nicely combine materials with new methods of measuring things. And also an advantage of the system is that now, I mean, MEMS are really fancy and very nice, but it's also really nice that here you do not need any electric connection with your system. Even if you want to have it in a liquid environment or something, it would still work. Okay, so to continue, so this was many things about shear viscosities. Now I want to make a small detour about how I can measure elongational viscosities. And this is also not very spectacular, but actually quite nice, is we can reproduce these droplet detachment also in microfluidic flows. And there were some people actually here that work on droplet production in microfluidic devices, which is actually something very common to do. So what you do is that you actually have what is called a flow focusing geometry. You have a central channel and two channels that come from the side. And the two channels that come from the side, you can hardly see them here. They're actually here and there. So a fluid will come from the sides and we actually pinch the fluid when it goes through here. And in this case, it's a polymer solution, so we actually create this long thread. If you do this for a Newtonian fluid, typically you use that to produce droplets in a very controlled way. And this then again is very comparable to the droplet detachment experiment, and you can see that you have this increase in elongation and viscosity with the same shape that you saw before. But what is nice here now is that actually by tuning the speed or the force, the strength of the flow focusing, you can decide what is the epsilon dot that you want to achieve. Contrary on the experiment where capillarity actually pinches, where actually surface tension dictates the rate at which you will work. So that's a nice way to measure elongational viscosities. Another possibility is the following one. It's actually something that comes again out of the group of Cargese-McKinley, which I think really uses very nicely what you can do in microfluidic flows. So we've heard that actually a stagnation point is a very good way to produce elongational flows. But the question is, how do you produce the best elongational flow in a microfluidic device? So when I showed you the experiment with the DNA molecule, it was just a square channel, right? So we had just had something that looked like that. So we have the stagnation point here, and we imagine that very close to the stagnation point, I will recover my hyperbolic flow lines. But certainly there's many places in the channel where what I will have is very far from the hyperbolic flow lines. So the group of Cargese-McKinley actually set out with the idea to numerically optimize the shape of the channel to obtain in the center of the channel something that was as close as possible to a purely elongational flow. So it sounds a bit trivial. You would say, well, the only thing I will do, I will draw a hyperbolic flow line and then I should have everything. So the thing that you need to take care of here is that you have a condition at the boundary of your channel where you have zero velocity. So if you draw a hyperbolic flow line, it doesn't mean that the fluid will exactly follow the hyperbolic flow line. And what the geometry that came out of the optimization process, you see these kind of ears here on the side. And what my interpretation of these ears is that they actually locally create a slip boundary condition. Right? Because you can see that here you can actually follow the hyperbolic flow lines quite nicely, because you do not have the zero velocity condition of the wall, because you have these ears that are filled with liquid, so we create a slip boundary condition. So by using this optimization procedure, they actually created this flow field, and they did another trick. So actually they did not want what we normally have in a very shallow channel, that actually you can draw whatever you want on your channel, but you will always have the shear dominance of what happens between the two plates. But what they really wanted to measure is what happens in this flow. So what they did is that they put the top and bottom wall as far away as possible. Okay, so it seems a bit contradictory, but to create a perfectly 2D flow, you need to have your walls very far away, because then you don't feel them. So that's how they created the flow geometry, which already I think is something that is very interesting and very connected to microfluidic flows. But then they had to measure these elongation and viscosities. And they did two things. First of all, they did the classical thing. They measured velocity and pressure difference. But also this, they did it in a quite clever way. Because even if they have an optimized system, the area where you really have an elongation and flow compared to the tubing and everything that you have around is relatively small. So they use their device in two different ways. So sometimes they will have flow going in through one arm and going out through the other arm. So they close two of them. So you have a pure shear flow in your system. And this is your zero state. And then they use it actually in the geometry where you have the elongation and flow. And what they will do is that they will compare the pressure difference between the two. And only the higher pressure that you measure in the elongational configuration is the part that is responsible for the elongation and flow. So that's one thing. And the other thing is also that they use the method where you do not need to measure pressure difference. And there's an effect that is called birefringence that maybe came up sometime during the summer school already, is that actually when you stretch your polymers, it will actually lead to retardation in polarized light when it goes through your sample. So it's a way that you can optically observe your sample. You measure the importance of these birefringence, and this is the local measure of the stress. So it's especially nice if you have systems that are very dilute and where the signal that you recover is very small. So if you need to measure stresses macroscopically or via pressure, your resolution might be really bad. But if you can measure it microscopically, you circumvent all of that and you have a direct measure of your stress. And that's actually what is shown here. So it's these two different methods. So this is where you look at these two different types of pressures. And actually you need to look at these graphs. So this is, I think, the shear, and this is the total. So you see it sounds great, but the difference between the two pressures in the shear and in the elongation and configuration is quite small. So for your resolution, that's not so easy. And this gives these open points here, so you can see again extension of viscosity starting close to 3 times the solvent, and then actually increases strongly until it saturates. But the black points here are actually the points that come from the birefringence, and they have also some kind of calibration curve where the retardation measured from the birefringence can be linked directly to the excess pressure, and you see that this gives actually a quite nice resolution. So it's a way to use something different to give you a measure of the stress. Okay, one more rheometer. So this is also a rheometer that uses in a quite clever way a different way to access local stresses. This is actually a wide channel that can measure shear viscosities. It has a very simple principle of working. You inject fluids through 2 arms. They will merge in the middle and then flow together in the channel. What you do is that they are injected with the same flow rate, and one of them you know the viscosity, and the other one you want to measure the viscosity. When they merge or when they meet in the main channel, they have to flow under the same pressure gradient because they're in the same channel. That means that if one of them is more viscous than the other, it flows under the same pressure gradient, it will flow more slowly than the other one. But we know that it needs to accommodate the same flow rate. So the one that flows more slowly will need to take more space to be able to accommodate the same flow rate. So by just measuring how much space in the channel is occupied by each of the fluids, I have a comparison of the viscosities of the 2 fluids. And that is what is represented here. Obviously, there's a little bit of approximation in the system, but basically, if your channel is very large and the height is very small, this is a very good approximation if your viscosities are not too different. And what you do here is that instead of measuring yourself the shear stress, you actually compare the shear stress to the shear stress in a fluid that you know, And this also allows you to get a very good resolution. And the small detour I will make here is actually to show you an example where we used the system and where we really wanted to measure very small modifications in the shear viscosity, and it was possible due to the use of the system. And the detour I want to make is to talk about the viscosity of active suspensions. So it's, for once, it's not a polymer, and you will see that actually this violates all thermodynamic rules in the sense that now locally you add something to your system that can locally inject energy into the system. But this is, I mean, I'm sure you've all heard about active systems. It leads to many, many, many very interesting phenomena. But here I want to talk about the fact what happens if I add this into a solution, what happens on the viscosity. And I will first show you the film. So what you can see here is a swimming E. coli under the microscope. And we talked over breakfast about the tracking technique. So together with colleagues in the lab, we have developed a technique that allows us to follow, with the microscope stage, the swimming bacteria in a microfluidic device. So for those of you who are not familiar, so an E. coli is actually something that has a head and a helicoidal flagellum. And the helicoidal flagellum will rotate, and this rotation will push the E. coli. So why does the E. coli swim with this strange way? Is actually it swims in the world of small Reynolds numbers, so in the fully overdamped system, so it cannot use inertia. So when we go to the beach and swim, we use inertia. I mean, we make one movement and then we continue. But the bacteria, if they would do that, they would just make one movement, they would advance, and when they put the arm back, they would go back and advance and go back. So that's something which is called the scallop theorem. So at small Reynolds number, a scallop could never swim. Right? So something needs to break the symmetry for an object to advance in a small Reynolds number world. And the symmetry here is broken by the chirality of the bundle of flagellum. Okay? So I will just show the film again. Maybe. So here what you can see is this bundle that actually rotates and it pushes the bacteria around. And something interesting that can also occur. What you might see at some stage, the bundle will open soon, I hope. Yeah, here. Maybe you saw it, it was quite fast. At some stage, one of the flagella was actually leaving the bundle, and maybe you saw that the bacteria has slightly reoriented. So that's really the mechanism that bacteria use to explore space. So when the full bundle rotates and is closed, it will actually push the bacteria in one direction. From time to time, one of the motors that rotates the flagella will rotate in the other direction. That will lead to an unbundling, and when things unbundle, it changes the direction of the bacteria, and they will continue to swim. So that's called a run and tumble motion. It is really the elementary movement of bacteria to explore space. When they're very happy, if there's a lot of food, they will change direction a lot. So they will stay very localized. And if there's nothing to eat, they will actually swim long distances before they change direction to explore space and find a better position. But for our purpose, let's just say, okay, I have these bacteria, they actually swim in the fluid, they locally inject energy by their metabolism to move. And if we look at what happens around this bacteria, so even if I don't shear it, so in a quiescent fluid, it will actually create a disturbance flow around the bacteria. And this disturbance flow looks like that. So that's a measurement of Ray Goldstein's group in Cambridge, and I think it's one of the most beautiful PAV measurements that you can imagine. So they measured locally the flow field of something that moves, and that is like 10 micrometers in length. Okay, because that I haven't really told you. The head is 2 microns, and with the tail it's 10. And I think it's a superposition of like 1,000 experiments. But what you can really nicely see that the perturbation of the flow field around the bacterium is like if it would push out fluid along its axis and suck in fluid from the side. So that's important to keep in mind, that you put a bacteria into the fluid, it will make that things are automatically out of equilibrium, it will locally inject energy, and what it does, it changes the flow field in that way. So there were many predictions of what would happen if I put that in a fluid on the viscosity, but very little measurements, mainly because it's very hard to resolve things. So we actually used this wide channel because by comparing fluids to each other, it's actually possible to measure viscosity differences that are as small as 10%. And the interesting curve that you should look at is the blue curve. So if we put the swimming bacteria into the solvent, what you can see, and you should be surprised by that, is that at very small shear rates, we can reduce the viscosity below the viscosity of the solvent. So this normally never happens, right? Everything you heard, I put something in the system and it will increase viscosity. So here it actually decreases viscosity. And then if I increase the shear rate, actually I cross the solvent viscosity and I increase things, and then I go back to the solvent viscosity. So the first thing we said, okay, this looks really, really nice, but is it true? Does it mean something? So we thought we need to compare to non-motile bacteria. So it turns out it's not so easy to have non-motile bacteria, because if you just kill the bacteria with some kind of poison, they might explode or lose their flagella, etc. So in the end, we actually put them in a very cold environment overnight and actually didn't give them any food or oxygen, and they were like kind of sleeping. And then we get the black curve. So actually you see this effect is a real effect. It's there, and it's not an artifact of our remeter. So why does it look like that? So first of all, thermodynamically you would say it must be forbidden, but it's actually not forbidden here because I locally inject energy in the system. So I can indeed reduce viscosity below the viscosity of the solvent. And then why do I lose the effect if I move to higher shear rates? It's because it's how important is the activity of the bacterium compared to what I put as shear in the shear flow. So if I compare time scales, and I think that's kind of what I did here, the mean shear rate, if I'm where I actually see that I cross here, can be compared to the swimming speed divided by the size of the bacteria. So that we lose the effect here also somehow makes sense. And let me just compare to these results. So what we think is that maybe here we can see a small shear thinning of something that might be like an elongation, like an elongated rod, the dead bacteria. And when I put the active bacteria on top of that, here in this region the activity plays a role. So I have the decrease in viscosity, and then I actually recover what happens for the passive objects. It looks more nice on the simulations where you have the passive graph that I already showed to you, and here you actually have, the red graph, which is the graph for the E. coli bacteria. But I should try to explain to you why we think that this is possible. So remember, if you looked at the shear flow was this combination between rotation and this elongation and compression. So the elongation was actually oriented in a certain way. So the elongation was actually oriented like that. So if you manage to orient your bacteria somewhere close to this direction of extension, then your bacteria will locally help the flow by pushing in the same direction. And this is at the origin of the decrease in viscosity, that locally your bacteria will push in the same direction as the shear that you applied. Okay. Yeah?
Does it change with the concentration of the bacteria?
Yes, it does. So it changes with the concentration of the bacteria. In the first approximation, it changes with the concentration of the bacteria, like in a linear way. Like you would, all of these effects would do. So, because once again, that's the same type of normalization of the viscosity, it is proportional to the volume fraction. But what is really interesting in bacteria, if you go to even higher concentrations, you can have collective motion that appears, and these coordination of bacteria that they will actually swim all in the same direction can lead to very, very strong effects. So my colleagues have actually continued doing this on a small shear rheometer, not in a microfluidic device, and they tamed this bacterial superfluid, so you can go to things where the viscosity more or less goes away fully. I don't have, I have a little bit of 6 minutes, okay. Well, first, are there more questions on that? Okay, so it's again a very nice interplay between orientation of your objects under flow and the specific properties, which in this case are the activity of the fluid. So I will use the last minutes to go through, I'm not sure what I should tell you with in preference. Maybe we can, I think I'll comment on that, maybe shortly. So we had a lot of discussion about curved streamlines and what curved streamlines do to flows in the presence of normal stress differences. So there have been quite some observations of people where they looked at geometries with curved streamlines like a Taylor-Quet flow or a plate-plate setup, where they realized that the system got unstable even at very small inertia. So the question was, where can that come from? And it actually, interest was renewed into these problems when people started to work with microfluidics, because in microfluidics, actually, this can be an interesting effect. If you do rheology, you don't want your system to get unstable because you cannot measure what you wanted to measure, but in a microfluidic channel, maybe you want to have the instability from time to time because it allows you to mix things, which normally you cannot do in a microfluidic channel. So these studies that have been done actually in the 90s go back to, again, a criterion by Pactel-McKinley, where actually they explain the existence of these hoop stresses that we have already discussed quite a bit. If you have a curved streamline, you imagine that you stretch your polymer along the curved streamline, it will actually lead to a force that will pull inwards. Okay? And it's actually this pulling of the force inwards that can drive your system unstable. So for those who are familiar with inertial instability, so in the Taylor-Quet device, you can see exactly the same pattern when you go to very high Reynolds numbers, and in this case, they are created by the centrifugal forces. They will push fluid outwards and lead to actually these convection rolls. And in our case, it's the opposite. The hoop stresses will pull things inward. So you can, flows can become unstable at very small Reynolds numbers, driven by the Weissenberg number, by the viscoelasticity of the system. And actually, what we did in our experiments is that we actually used the onset of that instability to detect the onset of normal stress differences. And so it's again a way, we know that it's very hard to measure this on a conventional rheometer, where you can use a different effect here, the onset of an instability, to detect the onset of instability, of normal stress differences. And that's what you can actually see here. So to visualize, what we do is we use the same what you saw on the white channel. We inject in this time the same fluid from both sides. One is colored, one is not colored. And if the flow is laminar, and you need to believe me that this is a film, it will actually just nicely follow the flow geometry. But when the instability sets in, it's very visual that you can see that it actually fluctuates with the flow. And I think to stop, I will just show, if I have the right, one or two films, because obviously also I didn't go to the end of my talk. So I just want to show you some things transported in a microchannel, because I think that's what I promised. And I want to show them to you in this nice hyperbolic channel, again optimized, so you recognize these ears, where we can actually pull on things in a very controlled way here and push on things in a very controlled way there. And we actually constructed an experiment where we can follow things transported through this channel by tracking, by moving the microscope stage, despite the fact that this velocity will increase linearly with distance and decrease linearly with distance when we go here. And just to show you that we can do very nice observations. So this is a protein aggregate. So it was a collaboration with a pharmaceutical company, and we can, it's mainly to show you that we can follow and observe at the same time. So it will actually reorient. So it's maybe the question, how can we orient things? So this nicely reorients things. But for the rest, not many things did happen on this polymer. And then let me maybe jump to the DNA molecule. So the DNA, you've seen the DNA at the stagnation point, and people were pulling on it. So now we will actually follow the DNA while it's transported through the channel. And you can actually see that it's kind of coiled here. So now we cannot see the channel walls anymore because we work in fluorescence. And you see how it will unravel here, and this part will actually stay. So this is like 10 microns, the length that you can see now. And it moves through the channel. And then it's coiled again. Yeah?
So why did in the previous case it did not unravel, and in this case it did unravel?
Oh, because the thing I showed before was a protein aggregate. You mean this one?
Yes. So what is the difference?
So this is much bigger. This is like, I don't know, 50 or even 100 microns in size. It's an aggregate which has like a consistency, a little bit of a gel. So we were hoping to stretch it, but actually the elongation forces were not strong enough. Yeah, and I will just use my privilege of a speaker to show you one last thing. So maybe some of you have seen Jubo's poster. So I want to show you one last thing, which is an actin filament. So an actin filament is something that we all have somewhere in our muscles to move, and it's something that is a very elongated biopolymer, which can have lengths of about tens of micrometers, and can be considered a little bit like a rigid filament. But it actually shows thermal fluctuations when you watch it under the microscope. So this happens when you see it, or watch it under the microscope. These are like 10 or 20 microns, and I don't know if somebody introduced the persistence length. If not, I would just say it, because I don't think I have time. It was? Great. So in this case, the persistence length is about the same length as the filament, so it's a semi-flexible polymer. So if I put this one in the channel, it actually looks very different than the DNA, which was a very flexible polymer, and it looks like that, and then afterwards you're free. So what you can see is that when we start to move through this channel, we will actually stretch the filament against the thermal fluctuations until it gets completely straight. And then when we go to this part, it will be compressed and form these very beautiful structures, which in the end turn out to be helices. Okay, I think I really have to stop. Okay.